3.3, measures of relative standing and box plots. Key concept, this section introduces measures of relative standing, which are numbers showing the location of data values relative to the other values within the same data set. So we're comparing one number to another number in the set. The most important concept in this section is the z-score. We also discuss percentiles and quartiles, which are common statistics, as well as other statistical graph called a box plot. So here's z-scores. The z-score or standard score or standardized value is the number of standard deviations that a given value x is above or below the mean. So we're comparing some number to the mean. Z-score is calculated by using one of the following. So both of these equations are really saying the same thing. It just depends on if you're talking about a sample or a population. So the calculation says take your x number, whatever it is in the list, minus the mean. Remember, x bar is the mean, and divide by the sample standard deviation. Okay, so it's number minus mean over standard deviation. Well, that's what this says as well. It says the same thing. It's your number minus the mean over the standard deviation. It just depends on if you talk about a sample or a population. Round z-scores to 2 decimal places. Okay. I think there was a question on your quiz that people missed because of the rounding rules. I know the rounding rules are kind of tricky sometimes, but here we are, round to 2 decimal places. Properties of z-scores. A z-score is the number of standard deviation that number of x is above or below the mean. Z-scores are expressed as numbers with no units of measurement. A data value is significantly low if its z-score is less than or equal to -2. Right? Significantly low, significantly high if its z-score is greater than or equal to +2. If an individual data value is less than the mean, its corresponding z-score is a negative number. So when you get a negative number for the z-score, you know that number is less than the mean. Example 1. Which of the following 2 data values is more extreme relative to the data set from which it came? So you've got two different things to look at. All right, so let's look at this one first. The 4,000 gram weight of a newborn baby among 400 weights with sample mean x bar equals 3152 grams and sample standard deviation is s equals 693.4 grams. Okay, so go back and think about the formula that we just talked about for z-score. Z-score equals x minus x bar over standard deviation. It's just a straightforward application of that. So you've got this number. This is our x number, 4,000. And we're going to subtract the mean. That's 3152. And then divide by the standard deviation that they gave us was 693.4. So 4,000 minus 3152 divided by 693.4 gives us about 1.22. Remember they said round to 2 decimal places, so 1.22. Now let's do the same thing for this example right here. We've got an x number of 99 this time, so we're still doing the same formula, right? X number minus the mean over the standard deviation. So our number is 99 this time, and the mean is 98.2, and the standard deviation is 0.62. This time we get 1.29. Oops. So we just found the 2 different z-scores. Go back and answer the question. Which of the following 2 data values is more extreme? Well, we're looking for a z-score that's farther away from 0, I guess, right? Farther away from 0 is this one. So to answer the question, which of the two data values is more extreme, we're talking about the 99 number. 99 is more extreme than, what's the other number? 4,000. Now, keep in mind, you can't really compare the number 99 with the number 4,000 because it's two completely different contexts. But within each of those different things, the red example and the blue example, you can tell that the blue one, the 99, is more extreme because its z-score is farther away from 0. Using z-scores to identify significant values. Remember earlier we talked about something that was lower than -2 or higher than +2 as being significantly low or significantly high. So that's just kind of talking again about what we're talking about. Significant values are those with z-scores less than or equal -2 or greater than or equal +2. It's just kind of a picture of that same thing. Example 2 says, is a platelet count of 75 significantly low? We're going to need to calculate that z-score. The lowest platelet count in a data set is 75. Is that value significantly low? Assume that platelet counts have a mean of 239.4 and a standard deviation of 64.2. So just do the same thing. We're going to do that z-score of our number minus the mean divided by the standard deviation. Negative 2.56. Is that significantly low? Yeah, because that's less than -2, right? That's less than -2, so this is significantly low. So yes. We've covered a lot of slides, and all we've talked about so far is z-scores. I've only given you one formula, so keep that in mind for z-scores. Now we're going to talk about something else, percentiles. Percentiles are measures of location denoted P1, P2, up to P99, I suppose, which divide a set of data into 100 groups with about 1% of the values in each group. How we can find the percentile is this formula right here. Percentile of the value x is the number of values less than x. It's kind of weird. Divided by the total number of values times 100. Okay, so we're looking at the number of values less than x over the total number of numbers times 100. Number 3, finding a percentile. The airport Verizon cell phone data speeds listed below are arranged in increasing order. Find the percentile for the data speed of 11.8 megabits per second. So, first thing I would do is just kind of identify 11.8. When we talk about percentile, we want to think about, what percent of these data are below 11.8. Okay. And so you might be able to kind of common sense, you get a calculator out and try to figure that out, what percent of the numbers are below 11.8, but we can calculate it. All right. So one thing to do is count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. There are 20 numbers less than 11.8. Okay. There are 20 values less than, well, I guess I shouldn't have said equals, less than 11.8. So that's kind of an important thing to know. Go back and look at the formula. We're talking about the number of values less than our number. So we've got 20. divided by the total number of numbers. Well, if each of these rows has 10 in it, 10, 20, 30, 40, 50, there must be 50 total numbers. We don't have to count to 50. We can see that's 10 times 5. Okay, so the number of numbers times 100. 20 over 50 times 100. If you can reduce that fraction in your head, it's pretty easy to see that's going to be 40. Otherwise, use a calculator. That's going to be 40. Okay, so 40, the 40th percentile. Otherwise known as P40. P40. Okay, P40 equals 11.8. Okay, the number in the data set with 40% of the numbers less than it is 11.8. Okay, so all we did, yes, I know there were 20 numbers less than 11.8, but we found what percent of the numbers are less than 11.8. 40% of the numbers. Notation: N is the number of numbers. K is the percentile being used. So for the 25th percentile, K equals 25. L is the locator that gives the position of a value. For the 12th value, L equals 12. PK, or P subscript K, P sub K, is the kth percentile. P25 is the 25th percentile. So here's kind of a flow chart for how to do the stuff. First thing you want to do is sort the data. And then here's a little formula for finding the locator. Locator is K over 100 times N. K being the percentile, N being the number of numbers, right? And then I think what's weird is you have to ask yourself a question: is that L a whole number? And if L is a whole number, then you have to do this extra thing. The value of the kth percentile is midway between the elf value and the next value in the sorted set of data. Find PK by adding the elf value and the next value and dividing the total by 2. That's just finding the middle of two numbers. Kind of like when you do a median and there's an even number of numbers and you had to find the middle of the two middle numbers. That's kind of what we're doing in this case. All right. If L is not a whole number, change L by rounding it up to the next larger whole number, and PK is the elf value counting from the lowest. So it's actually easier if it's not a whole number. You will not need to memorize this, I don't think, but I don't know, maybe it helps to have it in front of you. I think it makes a lot more sense if you find an example. So example 4, converting a percentile to a data value. Refer to the sorted data speeds below. Find the 40th percentile denoted by P40. Okay. So P40. We want to know which number we're looking at here. Okay. Or in other words, we want to know the number that has 40% of the numbers below it. And if you think about it, we just did that problem in a different way, right? And so you should know the answer because we just did an example similar. Okay, but that's what we're looking for in this case. P40 means find me the number that has 40% of the numbers lower than it. Okay, so if you go back and look at that flow chart, it says sort the data, that's done. And then the next thing we need to do is find that locator, that L. So if we're doing this on that example, we want to go L equals, okay, what is it? K over 100 times N. So K is just that 40. We're finding the 40th percentile. So 40 over 100 times N was the number of numbers, that's 50. 40 times 50 is 2,000. Divide by 100, you're going to get 20. Okay. So what that means is there are 20 numbers below our number. Okay. There are 20 numbers below our number. So remember what the flow chart says. Is that L a whole number? Yes, it is. Okay. So if L is that whole number, then what we have to do is find the 20th number. Let's go back and look at this flow chart again. Is L a whole number? The value of the kth percentile is midway between the elf value and the next value. Okay? Elf value means the 20th value. Well, the 20th value is right here. That's the 20th value. So what we have to do is find halfway between the 20th value and the next one. And so this is not quite what you thought. You were expecting the answer to be 11.8. The answer is actually going to be 11.6 plus 11.8 over 2. That's pretty easy to do in your head. You're just finding the middle of two numbers. And that's 11.7. So P40 is 11.7. Now, I want to add in another example just because I want to show you what happens when L is not a whole number. All right, so I'm going to call this example 4B. Let's find P25. Okay, find the 25th percentile. So 25% of the numbers are below this number. So first thing we want to do is find that locator. L equals 25 over 100 times 50. 25 over 100 times 50. It's 12.5. Okay. So remember what it says in the flow chart. It says, is L a whole number? No. Change L by rounding it up to the next larger whole number. Here we are. Okay. So that means take that 12.5 and round it up to 13. Round it up to 13. And just find the 13th number. So that's 10, 11, 12, 13. That's the 13th number right there. P25 equals 7.9. I think that's kind of tricky because how you do the problem depends on if this is a whole number or not. If that's a whole number, you do it one way. If it's not a whole number, you do it a different way. But that's finding a percentile. Quartiles, oh no. Come on. Where'd it go? Quartiles are measures of location, denoted Q1, Q2, and Q3, which divide a set of data into 4 groups with about 25% of the values in each group. It seems an awful lot like we're finding the median. In fact, Q2 is going to be the median. All right. And you split the data in half, and then Q1 is going to be the median of the lower half, and Q3 is going to be the median of the upper half. It's going to look something like this. You're going to have a minimum number and a maximum number, and your median is going to be Q2. That's the median. And you're going to have a median here, which is Q1, and you're going to have a median here, which is going to be Q3. Right? So you're finding a couple of medians, finding 3 medians. Q1, the first quartile, same value as P25. It separates the bottom 25% of the sorted values from the top 75%. Q2, the second quartile, is the same as P50 and the same as the median. It separates the bottom 50% from the top 50%. Q3, the third quartile, same as P75. It separates the bottom 75% from the top 25%. Caution, just as there is not a universal agreement on procedure for finding percentiles, there's not universal agreement on a single procedure for calculating quartiles, and different technologies often yield different results. So that just means if you're using your TI or a computer program, Your answers might vary slightly. Here we have something called interquartile range. Interquartile range is just Q3 minus Q1. Semi-interquartile range, Q3 minus Q1 over 2. Mid-quartile range, Q3 plus Q1 over 2. And 1090 quartile range is P90 minus P10. All right, so keep that list handy. 5-number summary. This is going to be important for something we do later, but for a set of data, a 5-number summary consists of these 5 things: minimum, first quartile, second quartile, third quartile, and maximum. And that's just the picture that I drew earlier. You're going to have a minimum, you're going to have a maximum, you're going to have a Q2 in the middle, you're going to have a Q1, it's the middle of the lower half, and your Q3 is the middle of the upper half. That's your 5-number summary. When we find a 5-number summary, okay, minimum is pretty easy to do. That's 0.8. Okay. And we want Q1, let's skip that. Q2, let's skip that. Q3, and the maximum is also pretty easy because that's just 77.8. So your minimum and your maximum are usually going to be easy to find, assuming that the numbers are sorted and put in order. If they're not in order, it'll be a little bit harder, but that's why we want to sort them first. Okay, so the median, or Q2, well, I mean, we could do it as medians, or we could do it as percentiles. Honestly, I think it's easier to do medians, but let's do percentiles just so we can practice. Okay. So Q1 is like P25, and Q2 is P50, and Q3 is P75. This is not the easiest way to do this problem, but this is going to be good practice. All right. So P25. Remember, we want to find that locator first. So 25 over 100 times 50. It's 12.5. Oh, I just did that. I literally just did that. It's 12.5. Remember, if it's not a whole number, we round it off. We round it up to 13. And we take the 13th number. And the 13th number is 7.9. So Q1 is 7.9. And Q50. Q50 locator is 50 over 100 times number of numbers is 50. That's going to equal 25. All right? 25. Remember what to do if it was a whole number. Okay? You find the 25th number and the 26th number and find the middle of those two numbers. Okay? And that's the same way as what we would do with the median. If we're finding the median, there's an even number of numbers. You find the middle two and find the middle of the middle, right? And so that's what this is about right here when we go 13.7 plus 14.1 over 2. You can probably do that in your head without a calculator. Just find the middle. That's going to be 13.9. So Q2, whoops, that was supposed to be Q1 up there. Q1 was 7.9. Q2 is 13.9. And then the next one, P75, you're going to take locator, 75 over 100 times 50, which is the number of numbers. It's 37.5, which we're going to round off to 38. It's going to be the 38th number. That's 31, 2, 3, 4, 5, 6, 7, 8. That's your 38th number right there, 21.5. So Q3 equals 21.5. So we've got our 5 numbers, hence we've got our 5-number summary. Okay, those 5 numbers. Now, by the way, Q1, 2, and 3. I already mentioned this, but I don't know if it really sunk in. If you're just finding the median, you're going to say, well, here's the middle 2 numbers. I need to find the middle of that. That's Q2, right? And then once you're looking at the lower half, you've got the lower half of numbers is all of these right there. You would find the middle of those, and that's this. And then the upper half of numbers is going to be these. You find the middle of the upper half. You're just finding medians is all you're doing. If you laid them out all out in a row, it might be easier to do. Okay, but you're finding the Q1, 2, and 3. That's the same thing as P25, P50, P75, but you're finding those 3 medians. Boxplot, or box and whisker diagram, is a graph of a data set that consists of a line extending from the minimum value to the maximum value and a box with lines drawn at the first quartile, the median, and the third quartile. Basically, we're talking about a picture of the 5-number summary. That's what it is. Procedure for constructing it: find the 5-number summary, construct a line segment extending from minimum data value to maximum, construct a box or rectangle extending from Q1 to Q3, and draw a line in the box at the value of Q2. It's going to look like this. Okay. That's the minimum. That's Q1, Q2, Q3, and that's the maximum. Notice it doesn't have to be perfectly centered. It's not going to be perfectly centered. It just depends on what the numbers are doing. All right. One of the whiskers is probably going to be longer than the other whisker, and that's okay. Okay, so example 6 says construct a box plot. Well, these are the same numbers as what we had before. We had a minimum was 0.8, and Q1 was 7.9, Q2 was 13.9, Q3 was 21.5, and your maximum was 77.8. So we already did our 5-number summary, so we've already got those 5 numbers. Everything good over there? Okay. Those are our 5 numbers. We need to draw a picture of it. So you want to start with a kind of a line segment from the maximum, or from the minimum to the maximum. So 0.8, 77.8. Okay. Now, I think the hardest part about this is just kind of positioning the numbers where they would need to go. All right. We wouldn't put 13.9 right here on a number line because that's not halfway in between 0.8 and 77.8. So don't put it in the middle. You can eyeball it up a little bit, but you don't want to put it in the middle because 13.9 is not in the middle. 13.9 is going to be a lot closer to 0.8, so we might put it like, you can kind of eyeball it like maybe right there. All right. And 7.9 is even closer to 0.8, so that's like right here. And 21.5 is, it's not going to be halfway, but maybe it's right there. So what they told us to do is they told us to draw a rectangle with one end at Q1, which was 7.9. That was Q1. And the other end of the box is at Q3. And then you draw a line inside the box at Q2. So we've got our minimum, and we've got our maximum over here. So it's a picture of the 5-number summary. Hardest thing about it is just kind of lining it up how it should go. All right. That Q2 Q2 does not have to be in the middle, and it's not. What it's doing is saying 25% of the numbers are right here, and 25% are right here, and 25% are right here, and 25% are right there. It's splitting it into 4 parts, okay? So you don't need that 25 as a part of your answer. We go back to something we've seen before when we talked about like a curve, and we talk about this as being skewed right. And that always seemed backwards to me, right? When I look at this, my gut feeling says it's skewed to the left. But we call this skewed to the right or positively. Another way of looking at it is it has a longer right tail, or in this case, whisker. And what this shows us, this shows relatively few larger data values. Okay. This shows us relatively few of the high data values. If you look at the data, most of the numbers, you look, they're all like below 30, right? Most of the numbers are down in the 20s and teens or whatever, definitely below 30. There really aren't very many numbers up there towards 77.8. Okay, and that's what the longer right tail shows us. Skewness, already kind of mentioned it. A box plot can often be used to identify skewness. A distribution of data is skewed if it is not symmetric and extends more to one side than the other. So we already did that, right? So identifying outliers. Find the quartiles. Find the interquartile range. Evaluate 1.5 times that interquartile range, IQR. And in a modified box plot, a data value is an outlier if it is above Q3 by an amount greater than 1.5 IQR or below Q1 by an amount greater than 1.5 IQR. I think that's really hard to think about, okay? It's really hard to process that, and that's why I think we need to do an example, okay? So what I want to do here, and I know there's not a whole lot of room, but I want us to try to squeeze this in, okay? Squeeze this in on the same slide somewhere. We're going to call it example 7. Find outliers from example 6. So here are the steps for identifying outliers, but that's what we want to do. Outliers are like extremely high or extremely low numbers. So when you look at it, when you look at the data, sometimes you can tell maybe what number is way too high or way too low. Sometimes you can tell, but a lot of the times you can't tell because of how specific this formula is. Okay. This formula says something about 1.5 times the interquartile range. That's really hard to get a hold of. All right. So find the quartiles Q1, Q2, and Q3. We did that a minute ago, right? Q1 was 7.9, Q2 was 13.9, and Q3 was 21.5. Those were our numbers, our Q numbers, our quartiles from that last example. So step 2 says find the interquartile range. Well, that's Q3 minus Q1. So Q3 is 21.5 minus Q1 is 7.9. So subtract Q3 minus Q1, and that's 13.6. That is the interquartile range, all right? Now, a lot of times we think about range as being from something to something else, but that's the definition. That's the interquartile range, all right? 13.6. Step 3 says we want to evaluate 1.5 times that number. So 1.5 times 13.6. It's 20.4. And that's, that's kind of the important number right there. All right, that's the important number. So in a modified box plot, a data value is an outlier if it is above Q3 by an amount greater than 1.5 IQR or below Q1 by amount greater than that. Okay, so essentially what we have to do is say Q3 plus 20.4 and Q1 minus 20.4. All right, so Q3 was 21.5 plus that 20.4, 41.9. And Q1 was 7.9 minus our 20.4 is negative 12.5. Anything outside of those two numbers is going to be an outlier. Anything greater than 41.9 or less than negative 12.5. Okay, so if you look back at the numbers, what was it? 41.9? Anything greater than 41.9 is going to be an outlier. Negative 12.5, there is nothing less than negative 12.5. So there won't be any outliers on this end. But on the high end, I see 4 numbers that are all outliers because they are greater than that 41.9. So you might have been able to guess those 4 numbers were outliers, but it's kind of difficult. Okay. I'm going to go back and look at the highest 4 numbers. 43.0, 55.6, 71.3, 77.8 are outliers. Okay, which brings us to a modified box plot. Okay, and I really don't have a whole lot of room here. A modified box plot is a regular box plot constructed with these modifications. Special symbols such as an asterisk or a point is used to identify outliers that we just did, and the solid horizontal line extends only as far as the minimum data value that is not an outlier. Okay, so in the maximum data value that is not an outlier. So we want to take that box plot that we did before, and so it went from 0.8, but we don't want to go all the way up to 77.8 because that's an outlier. We only want to draw the box plot up to the last number that's not an outlier, 38.5. Okay, so we're going to draw this box plot to 38.5. And we'll still have 7.9 as our Q1. And that box is going to go to, oh, that's terrible. $21.5, that's our Q3. And the median or the Q2 is like 13.9. We're still going to have the same box and whisker plot, except it's going to stop at 38.5. And then we're going to have asterisks for our outliers of, what were they, 43.0 and 55.6, and 71.3, and 77.8. So we mark those outliers with little asterisks or dots. Okay, and that is our modified box plot.